All right, so today we're going to dive deep into something that's got me really intrigued.
Yeah.
This idea of using quantum computers to actually help us build better AI.
Definitely.
So it sounds kind of futuristic, right? Like quantum computers are this mysterious thing that nobody really quite understands.
Right.
But apparently they could hold the key to some pretty big advancements in AI.
Yeah, exactly.
Specifically, we're talking about what's called Quantum-Assisted Hyperparameter Tuning, or QHT.
QHT, yeah.
And we're basing this deep dive on an essay by Jorgo Schneepat
That's good.
called QHT, Quantum-Assisted Hyperparameter Tuning for Chi.
Right.
So to start off, maybe you could help us break down like the very basics here.
Sure.
What exactly are hyperparameters in machine learning?
Yeah. So hyperparameters are basically the knobs and dials you set before you train your machine learning model.
Okay.
Things like how fast your model learns.
Okay.
That's just called the learning rate.
Mm-hmm.
Or how many layers there are in a neural network.
Got it.
Or how many trees are in a random forest.
Okay.
And these settings, these hyperparameters, can have a huge impact on how well your model actually performs.
I see.
It's kind of like, if you're baking a cake, the hyperparameters would be like the oven temperature, the baking time,
Okay.
the amount of each ingredient you're using.
Okay, yeah.
You get those wrong, your cake's going to be a disaster.
Right.
Same thing with machine learning. If you get the hyperparameters wrong, your model's not going to learn effectively.
So it's like finding the perfect recipe for the AI, basically.
Exactly. Yeah.
But from what I've read, it seems like finding the right combination of hyperparameters is anything but easy.
Oh, absolutely.
And that's where the whole challenge comes in, right?
Yeah, it can be a real headache.
It's a huge search space.
Huge search space.
And the more hyperparameters you have, the worse it gets.
Right. It grows exponentially the more you add.
And so traditionally, how have people actually gone about trying to find these optimal settings? What are the kind of classic approaches?
Yeah, so there are a couple of common techniques that have been used for a long time.
Mm-hmm.
One is called grid search.
Okay.
And this is basically where you define a set of values you want to try for each hyperparameter.
Okay.
And then you just systematically test every single combination.
So you're basically covering every point on the map. But that sounds incredibly time-consuming.
It can be, yeah, especially when you have lots of hyperparameters to tune. You can easily end up running hundreds or even thousands of experiments.
Wow.
Which, can take days, weeks, even months, depending on how complex your model is.
It's like brute force.
Yeah, it's very brute force.
But not very elegant.
Not very elegant, no.
Okay, and what's the other one you mentioned?
Right, so the other one is random search. And this is a bit more, random.
As the name suggests.
As the name suggests.
Yeah.
Instead of trying every single point in the grid, you just randomly sample hyperparameter values from a defined range.
Okay.
And run a bunch of experiments that way. It's often more efficient in practice because you're not wasting time on combinations that are very unlikely to work well.
Okay, so it's a bit more like throwing darts at a dartboard hoping you hit a bullseye.
Kind of, yeah.
But maybe not as systematic.
Yeah, it's more of a heuristic approach.
Okay, but it sounds like even with these methods, it's still kind of a guessing game.
Can be, yeah.
And it's probably even more of a nightmare with these really deep neural networks that have just like a ton of parameters.
Absolutely.
So that's where this whole quantum thing comes in.
Right.
So maybe you can explain to us, like, what are the core ideas of quantum computing that actually make it potentially useful for this kind of problem?
Yeah, so quantum computing is based on some pretty mind-bending principles of quantum mechanics.
Mm-hmm.
One of the key ideas is this concept of superposition.
Okay.
Which means that a quantum bit or qubit can be in multiple states at the same time.
Okay.
So unlike a classical bit, which can only be a 0 or a 1.
Right.
A qubit can be both 0 and 1 simultaneously.
So it's like it can explore multiple paths at once.
Exactly, yeah.
That's pretty wild.
It is pretty wild.
And that's somehow helpful for finding the best hyperparameters.
Yeah, because it allows a quantum computer to explore many different hyperparameter combinations in parallel, rather than having to test them one by one like a classical computer.
So it's like having a massive team of researchers all testing different settings at the same time.
Kinda, yeah.
But all packed into this one quantum computer.
Exactly.
And then there's this other thing I've heard about, entanglement.
Right. Entanglement is another weird quantum phenomenon where two or more qubits become linked together in a way that their fates are intertwined.
Okay.
Even if they're physically separated.
So it's like they're communicating with each other instantly, no matter how far apart they are.
Yeah, it's kind of like that.
That's some spooky action at a distance stuff.
It is. It's one of the most mind-boggling things about quantum mechanics.
And this entanglement thing also helps with hyperparameter tuning.
It can, yeah, because it allows the quantum computer to perform computations on multiple qubits simultaneously,
Okay.
which can speed up the search process even further.
So it's like all these qubits are working together in some kind of quantum dance
Kind of, yeah. It's a very coordinated effort.
to find the best hyperparameters.
Exactly.
This is getting pretty deep,
Yeah, quantum mechanics is not exactly intuitive.
but it's fascinating,
Oh,
right?
absolutely. It's one of the most exciting areas of science.
So, okay, we've got these kind of basic building blocks of quantum computing, superposition, and entanglement.
Right.
But how do those actually translate into a practical algorithm for doing this quantum-assisted hyperparameter tuning?
Yeah, so there are actually a number of different quantum algorithms being explored for QHT.
Okay.
The one that's specifically highlighted in Schneppet's essay is called the Quantum Approximate Optimization Algorithm,
Okay, QAOA.
UAOA.
Can you give us a simplified picture of how that works?
Sure. So imagine you have this vast landscape of possible hyperparameter combinations,
Right.
and each point on this landscape represents a different set of hyperparameters.
Okay.
And the height of each point represents how well the model performs with those hyperparameters.
Okay.
So the goal is to find the highest point on this landscape.
The peak,
The peak, yeah.
the optimal set of hyperparameters.
Exactly.
Okay.
Now, QAOA works by using a quantum computer to explore this landscape in a very efficient way.
Okay.
It's kind of like having a team of quantum robots that can simultaneously explore different parts of the landscape, and they report back on the heights they find.
Okay.
And then based on that information, the algorithm guides the robots to explore more promising areas in the next iteration.
So it's like an iterative process of searching and refining.
Exactly, yeah.
It's not finding the exact peak right away,
No, not necessarily.
but it's narrowing down the search space very quickly.
Right, and because it can explore so many different options at once, it can potentially find a good solution much faster than classical methods.
Okay, so that's the promise of QHT.
Yeah.
But the essay also talks about some of the limitations of current quantum computers, right?
Oh, absolutely.
There's this term that keeps coming up, an IceQ era.
Mm-hmm. Noisy intermediate scale quantum.
Can you explain what that means and why it matters for QHT?
Yeah, so NISQ refers to the current generation of quantum computers,
Okay.
which have a limited number of qubits.
Okay.
And those qubits are also quite noisy, meaning they're prone to errors.
I see.
This noise can really limit the complexity and duration of the computations you can perform.
So it's like trying to run a sophisticated program on a computer that's constantly crashing.
Kind of, yeah, it's not ideal.
So how does that affect the practicality of using QHT right now?
Well, it means that we can't yet solve really large-scale hyperparameter tuning problems using pure quantum computation.
Okay.
But that doesn't mean QHT is useless.
Okay.
It just means we need to be clever about how we use it. So right now, a lot of the research is focused on hybrid approaches,
Okay.
where we combine classical computing with quantum computing.
So using the best of both worlds.
Exactly, yeah.
And what does that look like in practice?
So, for example, we might use a classical computer to do some initial pre-processing of the data,
Okay.
or to narrow down the search space to a more manageable size, and then we can use a quantum computer to explore that smaller space much more efficiently.
Okay.
And then once the quantum computer has identified some promising candidates, we can switch back to the classical computer to do more fine-grained tuning.
So it's like a tag team effort between classical and quantum.
Exactly.
Okay, so we're still in the early days of QHT,
Yeah, very early.
but the potential is definitely there,
Oh, absolutely.
especially as the hardware keeps improving.
Right, as the qubits become more stable and less noisy, and as we get more qubits to work with, we'll be able to tackle more and more complex optimization problems.
Okay, and so now thinking about the future of this technology, what are some of the specific areas where QHT might really make a big difference?
Yeah. So the essay mentions a few really interesting applications. One that's really exciting is in the field of deep learning.
Okay.
Deep neural networks are incredibly powerful, but they're also notoriously difficult to tune
Right.
because they have so many hyperparameters to adjust.
Right?
And QHT could potentially help us find much better architectures for these networks.
Okay, so it could lead to even more powerful AI systems.
Exactly, yeah.
And what about other areas beyond deep learning?
Right. So another promising area is reinforcement learning, which is a type of machine learning where an agent learns by interacting with its environment. This is used in things like robotics and self-driving cars.
Okay, yeah.
And finding the right hyperparameters for reinforcement learning algorithms can be really tricky.
Mm-hmm.
So QHT could really speed up the development of these kinds of intelligence systems.
That's huge,
Yeah.
especially with all the advancements in things like robotics and autonomous vehicles.
Absolutely, yeah.
Okay, so we've got deep learning, we've got reinforcement learning. What else?
Well, the essay also talks about potential applications in fields like computational finance
Okay.
for optimizing investment portfolios
Mhm.
and in drug discovery for identifying promising new drug candidates.
So it's not just about AI, it's really about using quantum computing to solve these complex optimization problems that show up in all sorts of different fields.
Exactly, yeah, it's a very versatile tool.
And it sounds like QHT is still very much in its research phase,
Yeah.
but it's moving quickly.
It is. There's a lot of excitement and investment in this area.
And with all the progress being made in quantum computing itself, it seems like it's only a matter of time before we start seeing some real-world breakthroughs.
Yeah, I think we're on the verge of something really big.
So to wrap up our deep dive into quantum-assisted hyperparameter tuning, what are the key takeaways you would leave our listeners with?
Well, I think the biggest takeaway is that QHT has the potential to revolutionize the way we develop and optimize machine learning models.
Okay.
By leveraging the power of quantum computers, we could potentially find better hyperparameters much faster, which could lead to more accurate, more efficient, and more powerful AI systems.
Right, and this isn't just some far-off sci-fi concept.
No,
It's
not
something that's being actively researched and developed right now.
exactly.
And while there are still challenges to overcome, especially with the limitations of current quantum computers, the progress being made is really encouraging.
It is.
And
Yeah,
it's exciting to think about all the possibilities that might open up as this technology continues to mature.
absolutely. It's a really fascinating time to be working in this field.
So for anyone who wants to learn more about this, I highly recommend checking out Jörg Okenpat's essay,
Definitely a good read.
QHT, Quantum-Assisted Hyperparameter Tuning for Chi-I. It's a great starting point for understanding the core ideas and the potential of this technology.
It is, yeah.
And with that, we'll wrap up this deep dive.
Sounds good.
Thanks for joining me, and thanks again to Schneepat for the inspiration.
Yeah, it was a great discussion.
And to all our listeners, thanks for tuning in.
See you next time.
We'll catch you on the next deep dive.